Picture this. You write a multi-threaded Python script, right? You want to speed up this massive data processing pipeline.
Oh, yeah, a classic scenario.
Right. So you deploy it to this really beefy, 8-core server. You're expecting the execution time to just plummet.
Naturally.
You hit run, and suddenly your application is actually running slower than when you just had it on the single thread.
It's the ultimate betrayal.
It really is. Welcome to the paradox of Python concurrency. I mean, it's a rite of passage for almost every developer trying to scale up a Python app. You try to build this perfectly timed orchestra, and instead you get, well, a massive traffic jam.
And it's incredibly frustrating, right? Because the intuitive solution is just throw more threads at the problem.
Yeah, exactly.
But that fundamentally clashes with how the standard Python implementation actually operates under the hood.
Yeah.
You assume you're, distributing work across multiple processors.
But you're not.
No, you're really just adding the massive overhead of context switching, like with absolutely none of the parallel execution benefits.
Which is exactly why we are jumping into this today. Our mission for this deep dive is to basically decode how to achieve true concurrency in Python. Like, how do you make an application handle thousands of network connections, crunch heavy math, and write to a physical disk all at the same exact time?
Without the whole system just completely starving for resources.
Right, without crashing. It's like trying to cook a massive dinner party completely alone. You're trying to chop vegetables, monitor a bubbling stew, and somehow greet guests at the door simultaneously.
Yeah, it's a total recipe for disaster if you don't know how to delegate.
Exactly. So to figure this out, we're dissecting this really brilliant architectural piece by Aaron Rose. It's from tech-reader.blog, and it's called The Secret Life of Python, How to Use Threads, Processes, and Asyncio Together.
And what makes this article so good isn't just the code snippets. It's the framing. Rose uses this whole narrative to map out these complex architectural concepts.
Yeah, the setting is great.
It is. We're placed in this very atmospheric Grand Victorian library in London. And it serves as a metaphor for a code base where, craftsmanship and architectural rigor are just everything.
Right, and in this library, we meet Margaret. She's this seasoned senior software engineer, and she's talking to her junior colleague, Timothy.
Poor Timothy.
Yeah, poor Timothy is currently staring down that exact concurrency paradox we just talked about. He built this thing called the Grandmaster Tournament Engine, and it is just hitting a massive brick wall.
Well, completely, because when you look at his requirements,
Yeah.
you instantly see why a standard, line-by-line synchronous approach is just doomed.
It's a total nightmare scenario.
It really is a perfect storm of competing resource constraints. So, first off, he has 5,000 live spectators connected to the engine.
Wow.
Yeah, so that means maintaining 5,000 open WebSocket connections, constantly pushing and pulling these tiny amounts of data.
So that's heavily I/O bound.
Exactly. The system is spending the vast majority of its time just sitting there waiting on the network card.
But the network is just one piece of it, because while the engine is holding all those 5,000 connections open, it also has to analyze these insanely complex chessboard positions in real time.
Right, the heavy lifting.
Yeah, we are talking deep minimax algorithms, evaluating millions of potential moves. That is pure, heavy, CPU-bound math.
And if that wasn't bad enough, there is a third requirement.
There's always a third one.
Always. Every single move, every spectator interaction, and every engine evaluation has to be persistently logged to a slow physical disk drive.
Synchronous disk writes.
Yep. Completely synchronously and without causing any latency spikes for the live spectators.
I mean, if you try to run this sequentially in just a single loop like serve a user, calculate a chess move, write to the disk, move to the next user.
It would be awful.
Those 5,000 spectators are going to experience latency in the tens of seconds, maybe even minutes.
Easily. Because the network waiting blocks the CPU math, and then the heavy CPU math blocks the disk. Right? It's a gridlock.
So this is where Margaret introduces the core architectural philosophy of the piece. She tells Timothy that he can't be a juggler anymore.
Right.
A juggler just relies on pure, frantic speed to touch every task sequentially. Instead, she says he has to become a conductor.
A conductor of an orchestra.
Exactly. He needs to coordinate specialized workers who handle very specific types of loads so they can operate in tandem. Margaret calls this the symphony hall architecture.
I love that analogy.
Me too. So let's break down the symphony hall, because she maps it directly to 3 distinct tools in Python: Asyncio, process pools, and threads.
Right. The 3 instruments.
Yeah. And she assigns the 5,000 live spectators entirely to Asyncio. She calls Asyncio the system's juggler. And just to clarify, she isn't saying the whole system is a juggler anymore, but that we delegate those network connections to a highly specialized juggling mechanism.
Which makes perfect sense because Asyncio is perfectly suited for this. It relies on cooperative multitasking rather than preemptive multitasking.
Wait, break that down for a second. Cooperative versus preemptive.
Sure. So in a standard threaded model, the operating system's scheduler just brutally interrupts threads to switch contexts. It just cuts them off. And that adds enormous overhead when you scale up to 5,000 connections.
Right, because it's constantly pausing and resuming everything.
Exactly. But Asyncio operates within a single thread using an event loop.
Which means the code itself is responsible for yielding control.
Yes.
So when Asyncio fires off a network request to a spectator, it hits an await keyword. And that keyword basically tells the event loop, hey, I'm going to be awaiting on a network packet for the next 50 milliseconds. Take back the thread and go do something else.
Right, and the loop instantly pivots to the next spectator whose data has actually arrived.
Right.
It never just sits there idle, waiting on I.O.
It's so efficient.
Astonishingly efficient. But using these underlying C-level mechanisms, think like epoll or queue, this single-threaded event loop can monitor thousands of file descriptors simultaneously.
Wow.
Yeah, and it only wakes up the specific Python coroutine that actually has data ready to read or write. It uses hardly any memory.
But, and I feel like this is a massive but, for anyone listening who writes backends now, Python Asyncio only works if the tasks actually yield control, right?
Well, absolutely. That is the catch.
Like if Timothy takes his heavy CPU-bound chess algorithm and just drops it straight into the Asyncio event loop, he ruins the entire architecture.
Completely ruins it. Because of the cooperative nature of the loop, if a chess calculation takes, say, 3 seconds of pure CPU processing to evaluate a board,
then the event loop is just blocked for those entire 3 seconds.
Yep. The await keyword is never reached. And in that time, the network buffers for all 5,000 spectators fill up, connections start dropping, and the entire system starves.
Which is exactly why Margaret introduces the second section of the Symphony Hall, the process pool. She dubs this the muscle.
The muscles, I like that.
Yeah. And this is strictly reserved for the heavy CPU-bound chess calculations. The article really emphasizes that the process pool is required here because it is the only way to, quote, break the GIL.
Ah, the infamous GIL. We really need to be very precise about what the Global Interpreter Lock, or GIL, actually is.
Please do, because I think it's deeply misunderstood.
It really is. So CPython's memory management relies heavily on reference counting to know when to garbage collect objects, basically keeping track of what's being used.
Okay.
If multiple native threads were allowed to increment and decrement those reference counts simultaneously, you would get race conditions. And that results in massive memory leaks or just instant crashes.
So to prevent that, CPython basically enforces a mutex, a lock.
Exactly. Even if you have a massive server with 16 or 32 physical CPU cores, the GIL dictates that only one thread can execute Python bytecode at any given moment.
Ah, so that is why our hypothetical multi-threaded script from the intro ran slower.
Bingo. You had multiple threads fighting over a single lock. You're adding all this context switching overhead, but you're still essentially running sequentially.
That makes so much sense. And that is why Margaret points Timothy to the multiprocessing module.
Yes. A process pool completely sidesteps the GIL by abandoning the concept of threading for CPU work altogether.
So what does it do instead?
Well, when you spin up a new process, the operating system basically forks the Python interpreter. You are literally creating a brand new, completely independent instance of Python.
Oh, wow.
Yeah, with its own memory space and its own dedicated GIL.
But wait, I have to push back here on the practicality of that.
Sure.
If spinning up a new process means copying the entire interpreter and its memory space, isn't that a massive architectural risk? Like, if Timothy's chess engine is loading gigabyte-sized memory-mapped arrays to analyze historical board positions, isn't he going to just blow out the server's RAM the second he scales up to 5 or 6 concurrent processes?
That is an incredibly valid architectural concern.
Yeah.
And it brings up the hidden cost of multiprocessing, which is interprocess communication, or ITC.
Okay, IPC, yeah.
Oh, you used an analogy here. Think of threads like multiple workers standing around one shared whiteboard. They can communicate instantly because they all see the exact same data in memory.
Right.
Processes, on the other hand, are like putting each worker in a completely separate, locked room with their own private whiteboard.
Okay, I see. So there's no chaos and no lock contention. But if worker A needs to send a complex board state to worker B, They can't just point at the whiteboard anymore.
Exactly. They have to write the data down, slide the paper under the door, and have worker B copy it onto their own board.
That sounds slow. So in Python terms, what is that?
In Python terms, you have to serialize or pickle the data. Send it across an OS-level pipe or socket, and then unpickle it on the other side.
Wow.
Yeah, that IPC bottleneck can easily negate the benefits of parallel execution if you're constantly passing massive data sets back and forth.
Which is why Margaret gives Timothy a really rigid rule. Respect the memory. She treats processes as these highly expensive, dangerous tools.
You don't use them for lightweight tasks.
Right. You isolate the heavy math. You pass the absolute minimal amount of data required, say, just the current board coordinates, into the process pool.
Just sliding that tiny piece of paper under the door.
Exactly. The separate room crunches the CPU, heavy lifting on its dedicated core, and then passes only the final result back under the door to the main app.
You only utilize the muscle when the computational cost heavily outweighs that IPC and memory overhead.
Makes sense. Which leaves us with the final requirement of Timothy's engine, logging everything persistently to a slow physical disk.
Right.
And this brings us to the third tool in the Symphony Hall, threads, or as Margaret calls them, the helpers.
The helpers.
Now, hold on a second. We just established that the GIL forces Python threads to execute one at a time, making them totally useless for parallel processing.
We did.
So why are we bringing threads back into the architecture for disk writes? If the GIL is still there, aren't we just introducing the same lock contention we literally just escaped?
So this is actually one of the most elegant quirks of CPython.
Okay, color me intrigued.
The GIL is only held while executing Python bytecode. But when your Python code makes a system call to the underlying operating system.
Like writing to a disk.
Exactly. Like opening a file descriptor and telling the hard drive to write a block of data, the Python interpreter actually releases the GIL while it waits for the OS to finish that physical I/O operation.
So the thread essentially says to the bouncer, hey, I'm going to be waiting on the spinning magnetic disk for a while. Someone else can use the interpreter.
Precisely. Because disk I/O, much like network I/O, is heavily bound by latency, not CPU cycles. And because threads share the same memory space, remember our shared whiteboard,
Right.
they are incredibly cheap to create compared to processes.
Okay, this makes perfect sense for logging then, because you don't want to use Asyncio for standard synchronous file writes.
No, because blocking file I/O will just stall the event loop.
Right. And you definitely don't want to use a massive memory-heavy process just to write a simple text string to a log file.
That would be totally overkill.
So you toss the log data to a lightweight background thread. The thread calls the OS write function, releases the GIL, and just quietly waits in the background.
Yep.
And it does that without disturbing the heavy chess math or the 5,000 WebSocket users.
So you now have this complete specialized orchestra. You have Asyncio efficiently multiplexing thousands of network sockets on a single thread.
The juggler.
The juggler. You have the process pool bypassing the GIL to dominate the raw CPU cores for the chess algorithms.
The muscles.
The muscles. And you have the thread pool acting as these low memory helpers, handling the synchronous blocking I/O of the disk writes.
But having the instruments on stage doesn't mean they actually know how to play the symphony together.
Oh, definitely not.
The article emphasizes that deploying these tools without discipline is honestly worse than not using them at all. So Margaret enforces these strict engineering guidelines. And it starts with her absolute mandate, never block the juggler.
And this just cannot be overstated for anyone running production code. The Asyncio event loop is fragile.
Very fragile.
It is an illusion of concurrency built entirely on speed and yielding. If you accidentally drop, say, a synchronous request.getCall or a massive reject search,
Or complex JSON parsing.
yes,
Well,
directly inside your Asyncio loop, you have effectively paralyzed your server.
I've actually seen this happen in production. A developer added a quick synchronous database query into an async endpoint just to check a user permission.
Oh no.
Yeah. In testing, it was totally fine. But under load, that database query took like 200 milliseconds.
Which is an eternity for an event loop.
An eternity. Every time it ran, the loop froze for 200 milliseconds. Suddenly, thousands of concurrent users were getting timeout errors, all because of literally one blocking line of code.
It's a total cascading failure. That's why Margaret's rule dictates that if you are inside the Asyncio loop, you have to be paranoid about what you execute.
Paranoid is the right word.
The moment a blocking task appears, whether it's heavy math or a slow disk, right, you must use methods like loop .run executor to instantly offload that task.
Right, offload it to your process pool or your thread pool.
Exactly. The juggler must immediately return to juggling.
And then Margaret's second critical rule is all about resource life cycles. Context managers are kings. She mandates the use of with statements to ensure that pools and executors are managed cleanly.
This is so important. If you spin up a process pool executor with, say, 8 workers, and you don't explicitly shut it down.
They don't just go away.
No, those Python interpreters don't just disappear when your function ends. They become zombie processes.
Zombie processing.
Yeah, they'll just sit there in the background, consuming gigabytes of RAM, holding on to file descriptors, and basically slowly suffocating the operating system.
But by wrapping the executor in a with block, Python's exit method guarantees that the resources are joined and terminated correctly.
Even if an exception is thrown right in the middle of calculation.
It's like automated garbage collection for your infrastructure. It ensures the Symphony Hall is swept and the doors are locked after the performance.
And this level of architectural discipline leads directly to the climax of Aaron Rose's narrative.
Right, when Timothy finally runs the code.
Yes. He executes the refactored Grandmaster Tournament engine. And the article paints this highly satisfying picture of the system telemetry.
Oh, the HTOP dashboard.
Yes, the HTOP dashboard shows the CPU cores just lighting up sequentially as the process pool attacks the Minimax algorithms.
And the disk I/O metrics show steady, non-blocking throughput from the thread pool.
And right in the center of it all, the Asyncio event loop is just maintaining sub-millisecond responsiveness for all 5,000 connected clients.
The tension of that monolithic synchronous architecture completely dissolves. The components aren't fighting for the same execution thread anymore. They're actually cooperating.
It perfectly encapsulates Margaret's final philosophy for the specialist. Respect the weight, utilize the muscle, and maintain the flow.
Respect the weight with Asyncio and threads. Utilize the muscle with processes. Maintain the flow by never blocking the event loop. I mean, for everyone listening, when you sit down to architect your next system, this completely reframes how you approach Python.
It really does.
It dispels that tribalism that developers often fall into. You know, people declare themselves Asyncio purists and try to force the event loop to handle CPU bounds.
Or they default to multiprocessing for literally everything,
Right.
and then wonder why their cloud bill is so high.
Exactly.
It requires you to intimately understand the underlying mechanism of the task in front of you. You aren't just writing sequential instructions anymore. You are deeply engaged with the operating system, memory management, and process schedulers.
You are, as the source so aptly puts it, orchestrating reality.
Orchestrating reality.
Right.
It demands a shift from just being a coder to being a true software engineer. You have to understand why CPython requires a mutex for reference counting to appreciate when to break the GIL.
Right, and you have to understand the IPC overhead of copying memory spaces to know when a thread is actually the superior choice for I/O.
And when you master those mechanisms, the language just opens up. I mean, Python is frequently criticized for being slow in multi-threaded contexts.
All the time.
But this architecture proves that when deployed with precision, Python can orchestrate highly complex, massively concurrent workloads just as elegantly as languages compiled specifically for parallel execution.
It's a remarkable technical journey. Timothy closes his laptop thinking he has just conquered the system, but Margaret corrects him. She tells him this is just the baseline. The real work is maintaining this harmony.
Exactly.
So the next time a junior developer asks you how to make Python do 10 things at once, you won't just slack them a Stack Overflow link. You give them a symphony.
A system that breathes and reacts efficiently under immense pressure.
Exactly. But before we wrap up this deep dive, there is one final provocative reality I really want to leave you with. Something that pushes beyond the boundaries of Margaret's pristine Victorian library.
Okay, let's hear it.
We just explored a state of perfect static harmony, right? Asyncio handles the network, threads handle the disk, processes handle the math. It's a beautifully balanced equation, assuming the infrastructure and the inputs remain predictable.
And the real world is rarely predictable.
Right. So what happens when the environment of the Symphony Hall dynamically shifts mid-performance?
Oh, that's a scary thought.
Imagine a scenario where A rogue, unhandled exception in the deep math logic cascades through the process pool, just silently killing your worker nodes.
Mhm.
Or what if the cloud provider dynamically throttles your physical CPU allocation due to server load, and suddenly your IPC overhead vastly outweighs your compute
I mean,
capacity?
it would be disastrous.
When the very hardware beneath the code changes shape, or some unpredictable surge of malicious traffic poisons the event loop, does a conductor just wave the baton harder and hope the try-except blocks hold?
Probably.
Or does true senior engineering require building a system that can dynamically tear down its own symphony hall, resize its pools, and basically rebuild the orchestra on the fly while the music is still playing? Think deeply about the fragility of your executors the next time you deploy to production.